Alright, sounds good. I'd share a slide, but the truth is we don't exactly have one. The whole goal of this lesson here and the lessons for this week is just to answer any questions anyone has on anything we've covered so far. So, I guess in this case, I'm just gonna open it up to questions up front. See if anyone has any.
From Apple. While we're waiting for questions, do we want to do a recap of the material over the past few weeks?
That's a good idea, actually. Let's go ahead with that. So I guess let's go back to the first one real quick. Let's go back to the first week originally. As this has been, what is it, a month ago at this point? So, alright. So what have we covered so far? So I guess a couple high-level concepts. We did a brief introduction on what computer science is. In this case, the study of how computers utilize data, as well as computational systems. Also explained why computer science is useful, allows us to shape virtual and physical worlds around us. Most things nowadays are run-off code, so very useful skill to have. A couple goals of the class have been a high-level overview of some concepts in CFs as well as some resources. If anyone is wondering where these resources are that were mentioned in the first week, we currently have been posting a set of resources and examples along with the worksheet that gets posted each week. So within the actual Intro to CS forum, there will be the last few weeks' examples, as well as extra materials we have linked. All right. A lot of ways to make money in computer science. Companies, contracting, self-employment. Let me skip past this one. All right. I believe we had a hello world example on this. Okay, so this was the code from the first week. And now that we've gone through a little bit of this, we can actually explain what some of this does, right? So, print is a function. The value we are passing in here is a variable. In this case, it is a string data type. This is going to print hello Apple here. Next one will print I'm going to scream, and the next one will print ah. Okay. A few examples of some mathematical operations. So, value equals, right? So this is the variable name, as well as the equals is doing the assignment for it. 3 plus 4, performing an addition operation. 4 minus 3 in this case, we're performing subtraction. The little star symbol is performing multiplication. And the slash, what is the name for this? It's performing division. So in this case, it's print 1, 12, 1, and 7. All right. If there are any questions at any point, please stop me, interrupt me. I'm just doing a high-level overview until someone has a question on anything. We also covered variables as well as types. Waiting for this to load. So variable, abstract way to store a value, correct? So equals is the operator that is used to assign values to it. So for example, A equals 1, assigns 1 to the value. B equals 2, assigns 2 to B. C equals A will assign the value of A to C. In this case, that will print 1. Okay. Some types, and we actually did not list a type on here the first time we went through this, but there is also a type called a Boolean, which when we were doing the conditionals and everything, and we were trying to see if, for example, a value is equal to, greater than, less than, or whatnot, the value that's being returned by that statement is a Boolean value. So there is a data type that was not listed here, which is a Boolean data type. This is a list type, which we covered in a bit more detail last week, but fundamentally, list is just a collection of objects, collection of items. A float is a rational number with a decimal. A string is a series of characters, and an int is a whole number. And there is a function called type if you want to see the exact type of this. I highly recommend trying this on your own. All right. So, typecasting. So, let's say we want to do some addition, right? So, this won't exactly work the way we want to, right? So, 1 plus 1, that's going to return 2, right? Okay. However, B equals string of A. Okay, if we add strings together, we're going to get a string that contains 1 and a string that contains 2, that contains 1 as well, which is not going to print what we expect. It's going to print 11, and that is a horrible writing. We also did cover input, like how you would gather input from a user. We also covered functions a little bit. So function being a set of instructions that can be repeatedly used, right? So is this, I have my pointer out. Cool, okay. So, for example, a function is going to have a name, a parameter for inputs, return value, and a body. So let's show an example of this real quick. Okay, so in this case, we have 2 values being passed in, which are of type int. The function is named add. It's going to return an int. Function body is everything below this def, and the returned value is going to be whatever is specified by this return keyword. I am moving fairly quickly, so if anyone wants to stop me for clarification on anything, please feel free. All right. If anyone remembers this example, this is just an example of calling it. Not exactly the cleanest example on how to do it, but for example, if we wanted to pass the value from that was returned by this over to this over to this, we do that because what's going to happen is when add is called, it's going to pass the value over to the next function call. All right. Yes.
Question. So one of the previous slides had that return types and parameter types are optional.
Yes, you are correct. Depending on the language. In this case, Python, they're optional, but yes.
So what would be the reason why, like, specifying versus not specifying?
So one of the reasons you would specify it is one for your own, one I guess for your own sanity and for code readability, right? So for example, this, I don't exactly know by reading this immediately what it's going to return. I have to actually read this code block here to understand what's going to be returned. In this case, absolutely nothing's returned, but I don't know that until I read the code, right? Whereas a function like this tells me more explicitly, this will return an int. And I'm like, okay, I can use that information when I am calling it to make an intelligent decision on how to use it. It also means that I'm probably not going to do something incredibly silly, right? So, like for example, your IDE or your text editor or whatever development tooling you are using can actually use this information here to give you suggestions as well as to tell you when you did something wrong. Like for example, if I were to try to call add here and I were to give it a string as opposed to an int, it will actually error out. Like it's going to tell me, nope, dummy, you can't do that, and it's simply going to stop me from doing it. Which is very nice, because the alternative is I will find out when I run the program and I will crash the program. A lot quicker to figure it out when you're actually typing it out than it is to hit run and get the error back. But yeah, it's a good question, and I've seen code bases where people don't define any types. I've also seen ones where they define them everywhere. One is clearly more readable than the other, but I think that's, you know, that's more of a best practice than anything. Yep. Okay. Let me jump on down to the third slide real quick. Loops and conditionals on this. So this is going to be fun. And I feel like this was one of those slides where we did lose some people. So if then. On the previous slide, we briefly talked about there being a Boolean data type, right? So the way this would work is, for example, you have an if condition, right? If this is true, then it'll perform this action. Else, it'll perform this action, right? Okay. Really, all it cares about is that it gets something that equals true here, or false, so it knows to execute the other option, right? All right. It's like, for example, using the type called bool, we can pass in, we can set this to be true, and if true, it'll print this. In this case, it's always going to print the value true here, right? It's never going to print false because that's just not how that works. There is a what is not the term, a keyword you can place in Python, which is referred to as not, and I don't believe we actually use it on any of the slides. I can't spell. Pretend the first letter is an N. But what it would do is you would have something like not located on this conditional. So it would equate to if not this condition, right? So and what it will do is it will negate whatever value you have. So if the condition was going to equate to true, it's going to now equate to false. If it was going to be false, it will now equal true. It can be very useful for if you want to explicitly say, I only want this if condition to run in the event that this condition is not true, such as this value does not exist, or this value does not equal what the user provided. We did not cover that on any of the slides, but it's fairly useful keyword in Python. All right. A few common comparison operators. So equals equals. This is an equals condition. Less than condition. Greater than condition. Greater than or equal to. In this case, same deal, right? So basically this is greater than or equal to this, right? So greater than or equal to 1 is going to be true. 1 is not greater than 1, so returns false. You also have, for example, so here we're assigning a variable a to equal green, right? Okay. So let's say we do a does not equal here. So does not equal being a exclamation mark equals. This is pretty standard in most languages you'll work in. And what this will be is basically a if this does not equal this. In this case, green does not equal red. Yes.
Is there anything, I guess I don't specifically know for Python, but is there anything in terms of partial matching? Like I want to say some languages use like a question mark equals? I don't know if you can do
Question mark is a really nuanced one because it can also be used to like unwrap something. You mean like for like partial matching?
Yeah.
So do we have an example in the slide here? Because we have a pretty good example of a partial match in a string. Let me see if I can find it, because I thought we had one in here. Nope, we did not have one in here. Okay. I'm sure Apple can type an example in there that's a little bit more clear. But one of the things you can have, for example, is you can have something like this string value, right? Wow, I cannot type. I mean, not spell. Okay. So let's say, hypothetically, we had... So the keyword you're looking for is in, right? So in. So what this will do is if you have a variable defined on the left side, it will check to see if it is currently present in the variable on the right, and then it will return a conditional on that. That is how you can do a check in that. Ironically, in Python, it's the same syntax to see if it also exists in an object. Like I said, I'm sure Apple can give a good code example. I know we have some linked in the examples from week 3, we just don't have any in the slides. Hopefully that answers the question, though. Cool, okay. Have some fun with this. So, input, right? So we're going to take a user input, right? Okay, and we're going to immediately cast this to an int. Okay. So if it's less than 0, run this condition. If it equals 0, run this condition. If it equals 1, run this condition. Else, print this. Okay. So hypothetically, the way this would read is if this were greater than 1, because there are no conditionals where a value greater than 1 will meet, it will execute this last block. If it's less than 0, it's always going to execute this top block here. If it equals 0 or equals 1, it will print either the 0 block or the single block. You may also notice the use of elif here as opposed to else if. Python is a bit weird in this, in that it actually does make use of elif as opposed to just if else, which some other language, well, else. If else? Yes, if else, okay. Which some other languages are a little weird about. Okay. Also, this was not in the original upload, but this will be fun to show. So, if you wanted to have multiple conditionals, you can also do a match case statement. So, for example, in this case, we have x equals 4, right? Okay. So we're doing a match on x. Okay. And so in the event that we have it equal 3, it's going to print nothing to see here, move along. Otherwise, it's going to print adopted Blahi today. Okay, in this case, if it's 4. If it's 10, it'll print this. If it is none of these, then this is how you would handle a default case, is that underscore. That binary does actually translate to something, if anyone wants to have some fun looking it up. I actually don't remember what it is, because it's been a few weeks. Alright. So, loops provide the ability to perform the same set of operations over and over again. So we covered while loops, we covered for loops. Yeah, so we covered for loops. Let me go back to that slide. That's a pretty good slide, right? So the way a for loop works is we start. If we're the last item, then we end. Otherwise, we continue to loop around to the next item. Go for it.
Pun intended. Looping back to if, else, and elif. Question: what does elif do? Like, what's the difference between elif and else?
Elif, what it does is in the event. Okay, so this is partially an optimization, the way it's implemented, right? So when your code is also partially a logical thing. So when the code is running, it's going to evaluate this entire conditional block under the hood, right? So what it's going to do is it's going to check first that the if condition is true, right? In the event the if condition is not true, it's then going to start searching for elif conditions. It will ultimately hit the else condition if none of the elif conditions turn out to be true. Hopefully that clarifies it a little bit. So I guess more of the clarification is elif in this case is just a second else, not else. It's just a second if statement you can use. It's just if you want it to be in the same block of checks, you would need to use elif, right? Functionally speaking, there's nothing here that stops you from just putting another if in place. It won't be very performant, it won't be very optimized, and it's going to be a little harder to read because what Python will do is it will proceed to check every single if, but technically it'll run. Just may not do exactly what you expect with the else condition bottom. Hopefully that makes sense. Cool. Yeah. Match case is if you have a bunch of elifs, this is 100% a better way to do it. Match cases are fast, and match cases are also called switch cases in other languages are, and most other languages are fast, they're simple to read, and follow a similar pattern across most languages. So this, I would argue, is a lot easier to read than this. It's a very good question. All right. Let's take a look at this, right? So start last item, do next item. Okay, let's show a for loop here. This is going to be a for loop that iterates over a list of strings, right? Okay. First iteration, we're going to have w, or not, well, first iteration, we're going to have cat, right? So w is going to equal cat. Then we're going to have window equals w, and then we're going to have w equals window. Then we're going to have w equal defenstrate, I believe. I'm going to mispronounce this. Okay, and each time we're going to print the output of this. Hence the, in this case, this for loop is, the syntax for this would be for variable name present in the loop in the list you are going to iterate over. While loops are actually quite fun because they're intended, for example, if we're going to run forever. So a while loop will start, it'll do a conditional check if the condition is if the condition is one that's going to define that it needs to be exited, as in the true condition is now false, we're going to close the loop. Otherwise, we're going to continue this loop. For example, Here, this loop will run as long as x does not equal secret. By default, x is password, and we are going to request a new input or a new value for x every time we run this loop from the user. For those who may remember, a break statement is also a much cleaner way to write this. But we're just showing an example on this. All right. So for loops, if you know how much data you're going to be processing while you're coding it, you can use that. Otherwise, you're going to use a while loop if you don't know the exact number of iterations. That's just a general rule of thumb, right? It's like, for example, a while loop is going to commonly be used in a game, while a for loop might be used to iterate over a bit of data from a user. Okay. I'm going to move a lot slower on this one. And I'm also going to fully acknowledge that I don't know if the typos in this are fixed at this point. I forgot the first half of this lesson was reviewing. All right, cool. So, objects. Okay. I have to reiterate this. Objects are extremely nuanced. I personally have done a lot of functional programming over the years, so in functional programming we do not really make use of this very heavily. However, it's a very common approach, very frequently used to organize programs, so we're going to cover it here. No, the typo is not fixed on this. Okay, cool. So I apologize for any typos on this. The typos are fixed on the slides that are currently in the Discord. So as an example, you would have the way you would define a class is you define it with the keyword class, the name, specific members. For example, we have a member X and a member Y. If we wanted to add a function inside of our class, we would define that with def, and then same syntax that we would have for a function, except for we would have the self keyword present, and if we reference the self keyword, similar syntax to this in languages like Python, not Python, sorry, in languages like Java. You can, using this or using self, you can reference X and Y within our class. We also have, so I guess I'll show an example on how you create a new instance or a new copy of example. We just do this. Example, parentheses, parentheses. And what this will do is this will call a constructor and create a new copy of this object, which will be assigned to the myExample variable. I do want to acknowledge this is a typo. This is supposed to be myExample. But in this case, it would be myExample.x, which is 20. All right. I'm going to jump through this a little bit here. Okay. So class definition is done by the class keyword. Variables is done by, so you could have variables, for example, defined with, whatever your variable name is equals the value. Functions you define with the def keyword. And to create a new instance, you would just call the class name with parentheses. And that'll create a new instance of it. Alright, this is a fun one. So over here, we have two classes. We have a class referred to as animal, and we have a child class referred to as cat. Cat is inheriting from animal the way it is done. So, in this case, because it is inheriting, when we call the headpat method, we are going to print meow on this. If we were to call the headpat method on animal directly, it's going to say no human. Because most animals don't like being pat on the head. Alright. Any questions on any of that? Alright. So this is the topic that we did last week. Data structures. In full disclosure to anyone who is in that class, and is still confused, this class at a college level takes an entire semester to actually completely understand, and we only touch the high-level surface of it. So, honestly, of everything that was covered, this is, I would argue, probably one of the most one was probably I would argue this was the most complex one that had been covered so far. In fact, I would say it's probably the most complex thing in the entire class. So, to review this a little bit, we covered a few different types of data structures last week. We covered sets, lists, and what else did we cover? The dictionaries, I believe. Let me just go through the list real quick. So, we covered lists, which are functionally an array, right? And we're using lists pretty much whether or not we realize it, right? Because we have to, in order to do so, well, we have to use them in order to define any collection or group of data. As we had up to this point, we had been using a list. Unless we use an object, but in most cases we were using a list. In fact, the bulk of our examples still used a list. A list is sequential and indexable data, right? So it's fast, and it's going to be specifically as fast as the number of items you currently have in it. So the larger this list becomes, the slower the time it is in order to access a specific value you are looking for. So if you want to print what's currently at index 0, that's going to print 1. If you want to print what's currently at index 3 on list 2, that is going to print D, because indexes in Python start at 0. Lua, for anyone who has programmed in that, they start at 1. That is very fun, because you look at the code and you're like, why did this just crash? So to show us a little bit, index 0, 1, 2, and 5. This, of course, is 3 and 4. You can get really far with lists in terms of storing data. They're pretty versatile. So, you can easily add to a list. You can also quickly shorten from the list if you remove an item from the middle of the list much slower, because under the hood, this has to store all of these in order, right? So, Apple, Lucia, Laha, and Ivowich Rahaza, right? So, removing one of these in the middle is basically going to require those items to remain in order, which is a bit slower. Methods to add to a list. Append is the method that we use. Pop is the method that's used in order to remove an item from the end of the list. you can search in a list, it's going to be relatively slow. So for example, the in operator here, right? So I'm looking to see if EPL exists in names. Okay. So I know from the previous slide that EPL is very much in the list. In fact, they're the first thing in the list, right? So in this case, it's going to print EPL is still here. Now, if we remove EPL and we are deleting an item at the beginning of the list, which we should probably not be doing, but showing it here for the purposes of showing that you can do it, using the delete keyword here, we can delete at that specific index. All right. All right. We can also do slicing on a list. So slicing on a list is, and we actually have fairly good examples of this in the notes that were uploaded and the examples from last week. But as an example, it is the start index and the end index inclusive. Yeah, inclusive. So for example, this is going to be 0, 1, 2. So we're going to start at shield, and we're going to go to potion. We are going to stop before 4, in other words. If that sounds like a great way to introduce a bug, it is a great way to introduce a bug. I actually failed a coding interview once because I forgot that. Long time ago, but did it. Haven't forgotten since, but definitely learned my lesson. So, list of lists. There's a 2D list. One common use case for this is, say, a game board, right? Okay. So, for example, we have a list. We just have a list of lists because the list can contain anything. So the first index is the index of the list in use. The second index is the value in the list, right? So in this case, index 1, value 2. So this is going to select EPL. And look, we even have a comment there that says print EPL. Ah yes, hash maps, dictionaries. So, one of my favorite data structures. The way it works is you provide a key value and you provide a value, right? Python then under the hood runs it through a function to store it and handles all this organization on where it's going to store and handle it and keeps the mapping in place for you. So you can define a key and you can retrieve a value, or you can define a key and you can set a value in the map. Common way to add a value to a dictionary is through this syntax, as in birthdays and then the name of the key, assigning the value on the right side, right? So in this case, we are assigning for birthdays with Blaha, we are assigning this to October 13th. We can also delete it by using deletion. Similar, I think this is the same syntax we use to delete from a list. Very useful. Unlike lists, this is very fast to delete. There's no order guaranteed. Well, in most languages, Python does guarantee order. And is also very fast to add a key value pair to it. So, we said that they don't have order. That is correct as a general language term. In Python and more recent versions, they do preserve their order. Just for clarification on the notes that are in here. We also have sets. Functions very similar to a dictionary, except for it's guaranteed to be unique, right? So if I call .add, it's not going to add the value twice. So for example, adding cat, dog, and cat will only add one cat. Add being the method we use to add to it, remove being the method we use to remove from it. It's very good for preventing duplication whenever you're going over a collection of data. All right. Personally, of the ones listed on here that we're not covering, trees would be my favorite. But that is everything we've covered so far. So, and I realize that is a very, very quick go through all those slides and everything, but just to cover the high level on what we've gone through so far. Are there any questions on any of this? Any specific areas or anything? All right. We have a few minutes, and I was telling this story a bit, but I don't know if anyone. I was telling this story a bit, but I think this is a very good example of what not to do. Let's see if I can find the list I'm looking for. Okay. So keep in mind, this was many years ago, back when I tell the story, this was many years ago, back when web technologies were a lot less mature, a lot harder to use, and in general, you had to do some kind of obscure stuff sometimes. So we had a requirement on a project I was working on where we were basically told, build a website, we want to be able to navigate the whole thing with arrow keys. My solution, and reason I'm showing the 2D game board here, or I'm showing the list of lists, is I decided to store every element on the page within a list of lists. This is a great example of using the wrong data structure for the job. So while it technically worked for me, it did not exactly work perfectly. It was incredibly unintuitive and very hard to use. It was also very complex because anytime I needed to change an element on the page, I had to go into this data structure and I had to find the specific item that was here, right? Didn't work well at all. What we ended up doing instead, which is crazy now that I think about it to this day, what we ended up doing instead was actually getting rid of our list of lists, because this was over-engineered when we did it. And we ended up going with a different data structure, which was, what we ended up doing was something very simple. We actually went with a list. We went with a list, and if the user did a key operation, such as an up and down arrow, I guess the way I had the logic was row of elements being a single list, we would just skip them ahead by that number. So in this case, let's say there was 10 items, we would skip them ahead 10 elements in the array. And that was a far simpler and easier data structure to use. Yeah. So, going back to the point here, there is a working solution to every problem, there's an efficient solution to every problem. And sometimes you aren't going to know what the efficient solution is until you've already built the inefficient one that just happened to work. That's completely fine, that's just nature of engineering. There is a lot of work in the professional space, which we refer to as refactoring, which is going back through and redoing what we did the first time to verify we did it correctly, or specifically to fix what we did wrong the first time. Sometimes it's because we didn't have time to do it right the first time, sometimes it's because we didn't know any better, sometimes it's because we were half asleep the week we wrote it, forgot to tweak things like that. For whatever reason, that type of rework does happen, and it's normal, it's expected, and it's nothing to be bothered by. In fact, if you got it right on the first try, I'd be genuinely surprised, because I have yet to meet an engineer who will get this perfect every time. I can also tell a fun story with this. So, this is typically very efficient, but in Python and in many other languages, this will store whatever you give it. So if you give it an entire object or an entire class, it has to run this hashing function over that entire object, which is very, very inefficient. So I ended up doing this once with an object that I think had 101,000 keys, if memory serves off the top of my head. It took 45 seconds to build the object. It was supposed to take 45 milliseconds. Not exactly my smartest decision in the world. You know. But yeah. Anyways. So, every data structure has its strengths and weaknesses on it, right? Hash maps are very good at storing, say, simple values, right? So, for example, something that isn't going to be extremely expensive to hash, pretty valuable, pretty good use for it. But yeah, I do have one example here, one note, and we're not going to cover this specifically, but if someone is curious and wants to read into this more, one of the most common data structures you will find under the hood in a lot of applications, libraries, and the like is a tree. It's actually very common, even in very, very old video games, like especially RTS games, for the map to be represented by a tree. The reason being, the access times were fast, and you could do pathfinding with units across the tree very, very quickly. Specifically, the tree in use was typically B-star trees. There's tons of different data structures and different ways to approach a problem, and there are hybrid and customized solutions made by people over the years, or there are implementations that are sitting on top of a data structure or a combination of them in real-world practice. This area is literally something that takes genuinely years to completely understand. But we figured we'd start trying to cover it. I don't have anything to add. If anyone has any questions on anything. No questions? All right. Well, I guess we're good to call it. Have a good one, everyone.